Hello again, folks, in 113. Today we're going to be finishing up Chapter 9 by doing specifically Section 9.3. This is just an overview from last time and the time before. Okay. Today is Tuesday, November 16th. So per the schedule, we're covering 9.3, and we're right on schedule. Good. Okay. The packet that I have for you today consists of the following. This is an overview to acquaint you with the notations that we're going to be using today. All right, and these are different tools. You'll see the clock, the shorthand notation, and tables. Okay. This is just to acquaint you with the clocks. Using something familiar, 12-hour clock, like we use in the United States, we adapt that. I included a blank table like this for some terminology. It's an alternative way to get used to this. All right. This is, I'll have it labeled in Canvas, something that I would use specifically to answer example 5. You don't have to, of course. Here is a table, right, that we're going to fill in together. I think what I'll do is I'll have the actual filled-in table included in the PDFs, but better to go through the actual exercise to acquaint with the material. And then if you're not happy, I mean, with my explanation, you always have the book, of course. I swiped what I thought were the pertinent texts from the textbook. This includes terminology as well. And then there are the actual examples. There's quite a few of these. They're a little weird, so we'll go through the more interesting type at least. Okay. And I think that's it. There's just a lot of pages for this. Yeah, okay. All right, so if you're following along, do print this, and I'll explain it, and you can annotate. Get some water here. I'm running a little late today. Let me adjust the lights. I'll get busy. All right. Maybe before I turn on my camera here, let me refer back to this again. This is essentially where we've been, where we are, and where we're going. All right. Specifically, 9.3 is where we're headed today. But just to refresh your memory, here's some fun facts about these. All right, Section 9.1 was an introduction to Chapter 9, which is about something called systems. All right, a subcategory of systems are groups. They have to meet 5 criteria. All right, what we're to do with that, aside from the introduction, is to get acquainted with the terminology. Now, the thing that was interesting about Section 9.1 is that we were dealing with infinite systems, such as real numbers, or rather the natural numbers. And in contrast, what we were doing in Section 9.2 was discussing finite systems. Okay. Now, if you have a finite system, what you can employ, instead of simply writing everything out, is produce a table. Sometimes the table is given to you, and sometimes you have to make it. We're going to be doing that later again today as well. But it was more interesting to employ some rules using a table to decide whether something qualifies as a group or not. All right. What's the difference between these two? All right. Things that have finite systems and that include tables are cyclical. All right, and you'll see that in both of these cases. Section 9.3 will be employing tables as well. All right, and therefore finite systems that are cyclical. All right. The hard part of both of these sections, not to corrupt your opinion, is that they require you to sort of adjust to an arithmetic that's different than what we're used to. All right. Now, because what we're dealing with is cyclical, all right, we have to adjust. Adjust our idea of arithmetic. Because what we're going to see is not an infinite stretch of numbers as we would in an infinite system. Numbers that recur, right? There's a lot of repetition, i.e. it's cyclical. All right, so just be aware of that, right? If you see, especially if you're looking at the examples, anything that seems to defy all reason that we've acquainted with to this point, you know, since a little kid, I mean, just in the back of your head, say to yourself, okay, this isn't necessarily untrue, what I'm looking at, but it's indicative of a cyclical system. So we're going to see the same numbers again and again. Anyhow, what is most interesting about this section 9.3 where we are now is that we're going to get acquainted with notations, right? Which is more a written way of doing something rather than illustrative. Less of a picture, more of words, if you will. Okay? So here's, again, where we have been, where we are now, and where we're going. We're going to get used to reading notations. Okay? All right. And to do that, let me turn on my camera. It's a little segue, right? So there's 2 clicks. And adjust the lights. Okay, I have to move this card. Make up for you. Start with this. You know what? While I'm getting this adjusted, let me pull up my bootleg version of Paint here. And tinker with the camera just a wee bit here. Alright, that doesn't look too bad. Are we in the frame here? Looks like we're okay. That's blurry. Okay. I'm hoping my bulb holds out for the rest of the semester. I'd rather not have to replace it. So far, so good. Alright, before I get to the new stuff, let me just remind you of this information. It is perhaps a little bit more intuitive to have a picture, or at least the tool in question, to discuss or understand a system. So when we started talking about finite systems, we switched from the natural numbers, which are infinite, to clock 12 arithmetic. Now, here's a tool rather than a table or anything more verbal, all right, to help us get comfortable with that alien sort of arithmetic, clock 12 arithmetic, cyclical arithmetic, all right? A clock face, at least in the United States, runs from 12, all right, through 1, 2, 3, 4, 5, through 11, up to 12 again, all right? These are the hours of the clock, right? Even though we have a 24-hour day, right, we essentially limit ourselves to this character set, right? This set of elements, right? If you were going to list them in the roster style of elements, of a set of elements, right? You'd say 1, 2, 3, 4, all the way up to and including 12. Right? We don't have to be content with that. When the time is not right, you get a question about weeks instead. We could adapt this tool to that scenario. So what you see underneath this is a 7-week clock, if you can imagine, right? So what I would, in this case, I'm making it slightly more verbal rather than numerical. Rather than having 12 numbers on the face here, I've put the days, because we have in the United States Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. All right. We weirdly have we regard Sunday as the first day of the week, right, and Saturday as the last day of the week. Right? Perhaps weirdly to somewhere else. Right. Anyhow, if I were going to again write this in the roster style, I'm just using the abbreviations. You might see fancy braces, and then Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. All right. What we're going to be since we're talking about something called modular systems or modulo, is we're going to use numbers to represent the same thing. All right. So rather than have Sunday and it's the start of the week, we'll replace it with a number 0. Right? Makes it a little bit easier to handle arithmetic that way. And then go from there. So if Sunday is 0, all right, Monday, which follows it, would logically be 1 instead. All right? And adapted to this system, all right, starting with 0, all right, 0 would be the first element, 1, 2, 3, 4, 5, 6. And even though there are 7 total, if you counted these, because we're including 0, all right, the number 7 itself never shows up. All right? So do bear that in mind. All right? When we adapt any problem that you see, right, in this section to a modular system, the thing that follows the word mod, that digit, is telling you how many elements there are. Right? When you get into section Mat 114, the second semester of mathematical structures, we talk about base systems a lot. All right, this is the beginnings of that conversation, but we're at the tail end of Mat 113. Okay, so do bear that in mind. Okay. All right. In summary, we're familiar with a regular clock face, right? And this is how it would be divided up, right? But we can, if we want to, divide it up into a week instead of hours, all right? And if we go the whole 9 yards to adapt to section 9.3, we could replace the words with numbers starting with 0. Okay. Now, where would this be useful? All right. For word problems where they ask you something like, if today is such and such day, all right, day X, all right, what will it be so many days into the future, all right, Y days from now, all right? We have tools to assist us, all right? What I've already instigated in the conversation here is this clock diagram, all right? But what we can use alternatively instead of a clock diagram is these notations, which are called modular notations, all right? Just to give you a little heads up, we're going to get into vocabulary, but let me see if I could just sort of introduce some important concepts here. All right. First, all right. What you see in the box, with the sort of rounded corners here, A congruent B mod M, right, is a model that we will fill in a lot, right, in the course of the conversation, right? This is, right, well, these are the notation that we have to sort of get used to here, right? Right, what you see in the box here. Right? And all that it is if you were to read it out in English at least, is to say that the number here is essentially equal, but we will use the word congruent to A is congruent to B, or A is B essentially, right? In this peculiar system, right? A is B in this system. in mod m, the number of element system. Right? Congruence is something that you normally see in geometry, but it is that symbol that we use here. All right. All right. There. This is a summary as well. All right. How can you tell if things are congruent? Well, you could say with certitude that A is congruent to B if this situation arises. A divided by the modular, the base system, right? If A divided by M, that is this type of system, right? That's the number of elements. And B, the thing that you're looking for, all right, produce the same remainder. Once you divide them, if they produce the same remainder, you could say that they're congruent. All right. It's not really appropriate to say equal, all right, but they represent the same thing. All right. All right. We say congruent. Now, instead of writing something in this sort of shorthand notation, just as in lieu of using a clock, we could produce a diagram, right? Modular systems would be cyclical like this, so a table would be appropriate, right? In the case of mod, let's just say 7 in this case, because we're talking about days of the week here, Monday through Saturday, all right? The total number of elements would be 1, 2, 3, 4, 5, 6, 7. In the set, right? So therefore we call it mod 7, modular 7 if you like. And these would be the column headings, and these would be the same row headings here. And if you took the time to check the arithmetic, this is what you would end up with as a table, right? 0 plus 0 equals 0, 0 plus 1 equals 1, right? 0 plus 2 equals 2, and so forth. And what you, if you were to construct this from scratch, one thing that you would notice is that you can kind of spare yourself from having to do a lot of the intricate work because a pattern starts to show up, right? In a modular 7 system, the maximum number is the number 6, which represents, should be Saturday, right? If this is Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, you can't represent that with the number 7, right? Because we started at 0, right? So what happens when you have 1 plus 6, since this is addition here, you end up with a repeating number, right? You end up with 0 instead of the unique digit 7 because it's not part of the character set in modular 7. 7 is just a number of digits, elements, right? And then the same problem here. If you had 3 plus 5, right? You'll see that you end up with the number 1. That's the arithmetic that is kind of alien, and people who have never seen this before and have no introduction to it at all will go, what are you talking about? You know, how could 3 plus 5 equal 1? They do in this unique alien modular 7 system, right? Because it's cyclical. There is no number 7, right? There's no symbol that we have in a situation like that. All right. Anyhow, what you're going to see is essentially this. All right. We're going to take a mathematical system and translate it into what are called modular systems. So remember, a system is something that consists of what? in general, they have a set of elements, and they have a binary operation. Remember, in order to qualify as a system, never mind a group. All right. If we had something like clock 12 arithmetic, all right, the set would be 1, 2, 3, 4, up to including 12, right? And if it's arithmetic, it usually is synonymous with addition. Right. How would you translate that to a modular system? Right. We're going to keep that operation, basically. So it's still going to be an operation of addition. But what we have to do really is change the set of elements to start at 0 instead. So it'd be 0, 1, 2, 3, 4, up to, perhaps somewhat ironically, one number shy of the number of elements, so 12, right? And it goes up to just 11, okay? Right. Again, it's a little weird, but this would be regarded as a mod 12 system, and that's the abbreviation, mod, instead of saying modular or modulo. All right. All right. All right. Now, let's get some some vocabulary out of the way. I'll come back to that now. Right, there's really three concepts to sort of shore up. Let me zoom in just a wee bit here. Oh, my table's in the way. Not that. Never in the frame, I thought. All right. That looks as good as it's going to get. All right. Now, here's a first piece of terminology that is good to know. Right? We have the concept of something called a modulus. Right? A modulus is abbreviated by the symbol of lowercase m, which is kind of unfortunate in math because m gets used for so many things, right? But it is what it is, right? Essentially, right, this is the number of elements in the set. Right. When we get into the second semester, Math 114, what we'll be calling this is the base system. So you could kind of reserve that in the back of your head, but we haven't really introduced that terminology yet. Most fundamentally, basically, is to say that it's the number of elements in the set. Right? So if you see m is 12, all right, then that means there are 12 elements. That doesn't mean the number 12 actually shows up, though, because we start at 0. Right? Then there's this concept, congruence. All right. That's usually abbreviated as such. A is said to be congruent using this triple equals, if you will. It's really that symbol that is the congruency symbol, right? To B, right, in mod M. essentially two numbers are the same given certain conditions. They have the same remainder. Now, think about that. If you're talking about a remainder, that means you can divide somehow, somewhere. Okay. But when you see something like this, A and B are two distinct looking digits. Right? If they have the congruency symbol between them, it's saying that they represent the same idea, all right, but in the alien system, right, in a modular M system. Right? How do you check? You check via that this idea. Right? I'm a little short on space, so I'll put it here in reference to this. If A divide by M, which you would write this in the sort of traditionally English-speaking style, the division box, A in here is the dividend and M is the divisor. And B divide by M, which again would be written like this. If A divide by M and B divide by M have the same remainder when you divide them, right, then you could say A is congruent to B. Right. In the alien system. I prefer to say alien because it is more sympathetic, I think. Alright. Alright. Now, because I'm a little short on space here, what I'm going to do, and I hope you'll forgive me, is I'm just going to erase the top here and include a third piece of terminology here. Alright, so up here. This is why having a full-size classroom would be nice. You'll hear the phrase modulo, a modular class. This is essentially a set of numbers. Right, it's usually in a column in a table that have the same remainder. Which is to say, are congruent. Right? They don't look the same, but they represent the same idea. Okay, so a modular class is essentially a set of numbers that are congruent and have the same remainder. Right? Sometimes you're given a table that illustrates that, and sometimes you're not. Sometimes you have to figure it out yourself. All right? Anyhow, what is the advantage to all of this? Right. The advantage to congruence is you can perform ordinary arithmetic and then translate the remainders. All right, sorry for the sloppiness, but that in a nutshell is why we care about congruence at all, right? If we're dealing with an alien system and the arithmetic sort of defies the logic that we're used to, then by taking advantage of congruence, we can perform ordinary arithmetic, that which we're comfortable with, and then simply translate the remainders. Okay? I hope that that's legible. Right? If not, let me just throw this up here really quickly, and you can freeze frame if necessary. I thought I did that already. There you go. Okay. Still a little too short because my board is not that wide. Alright. Just to reiterate, the advantage of congruence is that you can perform ordinary arithmetic and then translate the remainder. Okay, how so? Well, if you divide by the modulus, the number of elements, twice, you could check to see if there's congruence there. Right? If A divided by M and B divided by M have the same remainder, then you could say with certitude that these two numbers are essentially representing the same idea. Alright. Now hopefully the trickiness to this is out of the way in terms of terminology at least. Now, to give you a feel for this, let me go back and do an example. And then I'll do the examples that are in the packet. Okay. Yeah, this is a little more meaningful. Here's to get your feet wet. Call it example 0. Right? If today is Sunday, what day will it be in 23 days? All right. This diagram that you see here might be useful in this case, so I'm going to kind of obscure everything else except for that. And hopefully that's not too much light, or too little light. All right. If you have a diagram that is a clock face where we replace the hours 12 through 12 again, with Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, right? We could pick the day and then arduously rotate around the clock clockwise that amount. All right, I'll do that as an afterthought just to verify that the answer is correct. All right, but what we could do instead is establish some information. We could adapt this basically to the Modulus system that looks more like that. Instead of having Sunday, you have a number 0. Instead of having Monday, you have a number 1. Right? I'm a little short on space, so I'm just going to have this much here. Right? But what I will do is I'll put the numbers that represent the days here. Right? Adapted to a modular system, Sunday is 0, Monday is 1, Tuesday is 2, Wednesday is 3, Thursday is 4, Friday is 5, and Saturday is 6. Right? This would be technically a mod 7 system, in spite of the fact you do not see the digit 7 in the set. There are 7 characters or elements total. Okay? Now, if Sunday is the day we're starting with, starting on Sunday, what number are we starting with instead of the word? If we're starting on Sunday, then we're starting with the number 0. And how many days are we looking to see into the future? What day will it be in 23 days? 23. So we're going to add 23 to this. And again, this is ordinary arithmetic at this point. And we'll see what we get. What's 0 plus 23? Actually, it's 23. Right? But we have to adapt the number that we have here to the modular system that would technically be mod 7, meaning that we need a character from this set of elements that would represent 23, because we're well beyond the maximum of 6 if we are dealing with 23. So what we're going to do is we're going to check congruence. Right? Remember, we're going to find the congruent element. Right? And we do that via this rule. If A divided by M and B divided by M have the same remainder once divided, then we could say that A is congruent to B, right? So, the A essentially in this case is this number. That's our A. Right? And what we're going to have to find is what B is. So, if we're dealing with the day of a week, 0 through 6 really, up to 0 again, we're going to just borrow the modular M system, the M number, right? If A is essentially 23, right, we need to know what this is when we're dividing. Right? I need a little bit of space, so I'm going to erase this much. In place of A, I'm going to use the number 23, unique to this problem. in place of m, I'm going to use the modular number, the number of elements, 7, because that's what days of a week would end up with. All right? And we'll see what we get. All right? Instead of writing it like this, though, 23 sort of linearly, what I'm going to do is write it in the more traditional long division style, so the box like so. 23 would be here, and 7 would be here. Okay. Now, how many 7s can you fit into 23 roughly? Right, this is why it would be good to know your multiplication tables. Roughly 3, right? And that would be 7 times 3, which is 21. And we'll see what the remainder is. The difference between 23 that was there and the 21 that we're using to subtract is the amount of 2. And this would be remainder 2. Right? What that means is that this is the b value. Right? In the model, A congruent B mod 7 or mod M, just to start out with a more no frills generalization here. 23 is the number that we're checking. This is the modular number. Sorry, I'm doing the old switcheroo here with my markers. The value for B would be the remainder 2. All right. A is congruent to B. All right. The way that the arithmetic, the division works out is that the remainder is 2. So therefore 23 is congruent to the number 2, right? In this weird alien system known as mod 7, all right? What does 2 represent in terms of the day of the week? 2 represents a Tuesday. Right? That means that if I were to check, and I'm going to, because it's always good to check. If I'm going to check starting on Sunday, 0, and then counting 23 days into the future from there, I should land on a Tuesday. All right. So let's do that the more sort of brute force way. All right. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Right? To have the clock, right, definitely makes a person feel a little bit more comfortable, right? But it's impractical the more numbers that you have to count. 23 days in the future kind of sucks to have to count around 23 times, you know, well, not 23 times 3 and a little extra, technically. All right. Take advantage of congruence. It's probably something, again, I don't want to corrupt your opinion, that you've never seen it before, so you go, I don't want to do that. All right? The more you do it, the more comfortable you get with it. It makes it a little bit more intuitive. Right? So don't fight it. Right? Give it a chance, give it a few problems, and you'll start to go, oh, I see what he's saying or what the book is saying. Okay? All right. All right, now let's shift over to the actual examples and go through them one by one, or at least as much as we can. All right. If you look at the examples now, which are here, I'm going to purposely try to just take out the thumbnail, come on, obscure most of it, and the solutions are there if you feel more comfortable just reading it. But let's go through this. Let me clean up my board a little bit and then chop it up into an appropriate amount of space to work. I'm going to rephrase this too, just as a good example. Example 1 is read as determine which numbers 0 through 6 the following numbers are equivalent to in modulo 7. Right? A more concisely written way of saying that is determine which numbers 0, 1, 2, 3, 4, 5, 6 are equivalent to the following in mod 7. If you're dealing with a modulo 7 system, this would have to be the character set, the elements 0, 1, 2, 3, 4, 5, 6. Okay? In order to decide what 60 essentially equates to using these digits only, right, what 84 equates to using these digits only, and what 412 would equate to using these digits only, we're going to use that congruence again. Right? So let me just duplicate the model here. And I try to use colors to illustrate, what is what. Right? Here's a model we're going to refer to. All right? A is congruent to B in mod M. So red I'm going to use to illustrate the modular number that I'm going to divide by. It's going to be a divisor essentially. A is the number that we have here, here, and here. I know that they unfortunately are called 60, A, 60, B, 84, C, 412, but it doesn't matter. Now, just to kind of confine things nice and neat, let me chop up a little bit of the space that I have here without breaking it. What a crash that was. I don't have much of a ledge here, unfortunately. Nope, no ledge. Okay. But we're going to do part A, part B, and part C here, here, and here. All right. That's the model, and here's congruence. A is congruent to B if A divided by M and b divided by m have the same remainder? Okay. So, the first number to check here is 60, right? Again, using the model labeling A, B, and M, all right? This is our A here, all right? 84 will be our A in example B, and A would be 412 in this other situation. Okay, so I had to use conflicting labels, but this is what we're doing here. We're dividing the number by m, the number by m, the number by m, and testing their congruence here. All right. So I'll superimpose with black here. All right. If 60 is the number in question here, then that's what I'm dividing. All right. If the modular system that we're dealing with has 7 elements, then that's what I'm dividing as a divisor here. Right? 7 goes into 60 roughly how many times? If you know your multiplication tables, then you know that 7 times 8 is 56. And the difference between these, therefore, 8 times 7 is 56, would be simply 4. That means that the remainder is 4. Right? Essentially what that means then is that A, forgive me for the temperamental way of writing this, but it's just for the sake of clarity. B, 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 7, M, M. If I substitute what I was working with and what I got into the model, we'll see what the case is, right? What these numbers are equivalent to using these elements only, right? Who is that? Probably a delivery. Pardon me 1 minute, I better check. Sorry for that. Okay. A in this case is 60. The B value is the remainder. So that's 4, and the modulus is 7. So essentially 60 is 4, right? In this peculiar alien system known as modulo 7. Alright, that's what we're getting at here. Translating this one, right? The A value here is 84, and we're still dividing by 7. Alright. 7 goes into 8 roughly 1 time, which is 7. And the difference is 1, carry down 4. 7 goes into 14 twice exactly, which is 14. and then you get a remainder of 0. So don't be deterred, right? What that is saying essentially is that 84 is 0, right, in this modular 7 system. Okay. All right, one more of these, 412 divided by 7. 7 goes in, no, into 4 is too small, but 7 goes into 41 roughly 5 times, which is 35. And the difference of 41 and 35 would be 6, bring down to 2. 7 goes into 62 roughly 8 times again, which is 56. And the difference is 6, which means that the remainder would be 6. Sorry. I'm boring even my computer here. Back up. All right. So, this number, 412, is essentially equal to 6. All right, that's the remainder in a modular 7 system. Okay? Takes a little getting used to, right? But it's not too bad. Look at example 2, because now you have a little bit of arithmetic, and rather than a number given to you, you have something that is a product or a sum or a difference. All right, and if I have to rephrase this again, I will. Okay. Now, in this case, now I'm jumping the gun here. Example 2 is to evaluate each of the following. Instead of having a figure given to you, you have a sum in this case, a difference in this case, and a product in this case. Right? Just figure out what those would be first, and then we'll figure out what their congruence would be. So, if this is A, and this is B, and this is C, we continue. I left the model up here for reference. I hope it's visible. I'm sorry for the lighting situation. But this collectively is our A in part A. Right? This collectively, the outcome difference, is our A in the model here. And this product is our A in the model here. Right. So, if what we have is 7 plus 8, right? What is that? And in this case we have 8 minus 5, and in this case 7 times 5. What do we get as an A value? Right. 7 plus 8 is 15 naturally, right? 8 minus 5 is 3, and 7 times 5 is 35. Right. So, notice what is blue represents our A here, just for the sake of continuity. What is this congruent to? This green is not the best color. Let me try another. What are these congruent to? In the mod system that we're using. that little extra labeling of parentheses, mod, and then the number. Helps to explain that you're not dealing with ordinary arithmetic. So in this case, we're dealing with modulo 9, which means that's essentially what we're dividing by. Okay. What essentially is 15 equal to in mod 9? What is 3 equal to? It's congruent, to be more technical, in mod 9. What is 35 in mod 9? All right. We're going to test by dividing by 9, essentially. So 15, 3, and 35. We're going to divide by 9 in this case, 9 in this case, and 9 in this case. And see what the remainders are. 9 goes into 15 roughly one time, right? Which is 9 itself, and the difference is 6. So this is a remainder of 6. That's the number. All right. 6. Nine does not fit into 3, right? But we're still going to do the arithmetic, right? So what would you say? You'd have to say 9 times 0, which would be 0. This times this, the quotient times the divisor, produces the number that you subtract here. And then you get stuck with the remainder of 3. So that's what it is equivalent to. 3 is 3. That makes sense, right? Because the number here is what would appear in the character set of mod 9. Remember, mod 9 would be 0, 1, 2, 3, 4, 5, 6, 7, 8. It would stop short of the number of elements 9, right? Because we start at 0, there is no 9 as a symbol, right? And I should be putting commas here, but I hate to do that because I think it makes it ugly, right? Anyhow, the number that we end up with as a result of this difference is one of the characters. So it should be kind of a duh, you know, like, yeah, 3 is 3. But don't be deterred. Do check the arithmetic here. All right, the ordinary arithmetic. All right. Now we're back to regular number that exceeds the character set, 35. 9 goes into 35 roughly how many times? 9 times 3 would be 27, and the difference would be 8. All right, so the remainder would be 8 in this case, and therefore that's what it's equivalent to. 8. 15 is 6, as goofy as that is, right? 3 is itself, 35 is 8, right? There used to be a commercial for, what was it? I think it was, might have been Carvel, the ice cream parlor, right? It used to say, Wednesday is Sunday, I think that was it, right? Which was a pun, right? Sunday is in ice cream, not the day of the week. Or whatever day they chose. Anyhow, Waka Waka. Right. It gets naturally a little bit more complicated. When you get to example 3, you'll see what I mean, because there's some preliminary work. Look at example 3 now, right? This is annoying, right? Again, not to corrupt your opinion, because you really do have to articulate the problem a little bit better than it was given to you. To make sense of it. So I may end up needing more board space than I have, so I'm trying to be strategically not erase too much. All right. Determine the positive number replacement, right? That would be less than the modulus for the questions, for the question mark that makes the statement true. So it's kind of an awkward phrasing. I don't really fault the person who wrote it, but because it's a question that exists in theory, but in English it's a little complicated. So one thing you're going to notice up front here is that in part A, the thing that you're looking for is here, right? Which is more or less what we just did, right? We were looking for the congruent amount, depending upon whatever this was. Right? In these other two problems, the missing part is on the A side of the model. All right? But it isn't just one thing, it's part of a difference in this case and part of a difference in this case. All right. So you're going to have to zero in on each of these. To try to make this more concisely writ, right? Let me try to rephrase here. Right? We're going to determine the positive question mark that would be less than the modulus m. Now the mod is going to change, the modulus number is going to change. It's 7 in this case, 5 in this case, and 8 in this case. The number less than the modulus. Okay. That makes each true. Determine the missing number that is a positive but simultaneously less than the modulus given in these cases that makes the statements true. Okay. Now, a couple of things to kind of get you in a good habit, right? If you're dealing with a mod 7 system, right, let's just check to see what the character set would look like in this case, right? If it's mod 7, it's going to be 0, 1, 2, 3, 4, 5, 6. It's a little bit bunched up, right? Notice that there's 7 characters total, right? That means that whatever this works out to be, it can only be something that conforms to this character set. We can't have some funny number that is not fitted in here, right? In this case, what is the character set supposed to look like if it's mod 5? It would be 0 again, 1, 2, 3, 4. There are 5 elements total, it starts with 0. Right? All modular systems do that. All right. In this case, we're mod 8. So it's 0, 1, 2, 3, 4, 5, 6, 7. There are 8 total. We start with 0 as we always do with a modular system. Okay. So what would happen if we just did it as it was given to us? 3 minus 5 would be equal to -2, right? That is not a positive number, right? It is less than the modulus number, which in this case happens to be 7, right? 7, 5, and 8. But it's a negative number. So what we have to do, the difficulty of this problem is that we have to sort of arrange for a situation where we have an equivalent to that, but not using that figure. So we're going to have to involve congruence again. All right. Let me remind you of this. All right. In mod 7, adding 7 results in numbers of the same modular class. That phrase is rearing its ugly head again. What is a modular class? Or modulo, like. They are numbers that they represent the same idea, right? So in this particular case, but you have 7, right? If you did 7 plus 7, you would get 14, right? If they're in the same modular class, that means that they have what? The same remainder. Right? 7 plus 7 plus 7 would be equal to 21. Right? All right. I'm a little short on space, so I think I might erase this, and it's not untrue. I want you to sort of save this thought, but I need the space. All right? In a modular 7 system, if you keep adding 7 to a figure, you're going to get something that looks different, but it represents the same idea. In a nutshell, it would end up having, if you divided them by the same modulus number, you'd get the same remainder. All right? Now, with that in mind, we have to get out of the situation of being negative here. Right? So we got to work basically on this figure. Right? Because of the way that this is arranged, you have a smaller number than on the left side of subtraction symbol than you do on the right side of it. That produces a negative, right? So we need to figure out something that's going to get us out of this negative realm here, right? So that's equivalent to 3, right? If I took the number 3 and I added 7, right? Because in theory, in a modular 7 system, if I just added another 7, I may get something that looks different in ordinary arithmetic, but it represents the same amount. They're congruent. They have the same remainders when you check them, right? If I added 7, right, what would I end up with? I would end up with 10 in that case. Right. Even though this is going to look weird, right, I'll verify this, but in this system, 10 minus 5 is going to produce a number which we have to figure out yet. In mod 7, that is going to be positive, and it's going to be less than the modular number. All right. What do you get if you did the ordinary arithmetic here? All right. You would end up with 5. It's not falling asleep. Now, the result that you get here is a character that shows up in the set in modulo 7. So just like earlier in example 2 it was, I believe, where we had 3 is 3, there's no reason to have to divide this, right, to figure out what the equivalent is if you want to. All right. I'll do it anyway, just for argument's sake. Right? If essentially we're looking for the equivalent here, in mod 7, what would happen if you checked this rule, the congruency rule here? If A divided by M, B divided by M have the same lambda, then you could say that these are congruent. Right? Well, if you did, just for lack of space, 5 divided by 7, right? 7 goes into 5, well, it's too small, so you would put a 0 here, right? And then the product of the quotient number and the divisor number would be what goes here that you subtract, right? 5 minus 0 would be 5 itself. That's the remainder of 5. That is the figure that would sit here. That's a little cumbersome, admittedly, right? The best explanation I can give, at least at this point in the conversation, is this, right? We were looking for this figure, right? And it ended up being 5 itself. Now, let's see if that conforms to the requirements here. Is the question mark a positive number that is simultaneously less than the modular number? It is. 5 is less than, is a positive, and it is also less than the modular number of 7. Right. Right. Why did I add 7 here? Basically to avoid the situation where I have a negative, because that's not meeting the requirement. Right? So I wanted the equivalent of this, right? That could be outside of the negative realm, if you will, right? So I added 7 to go through the cycle 1 extra, right? That produces a 10. If I do the ordinary arithmetic here, right, that's a 5. Right? Essentially, this side of this model that I've been using over and over again is the side that is ordinary arithmetic. And then we see what it translates to in what we might call alien arithmetic. All right, let's do more of these to get more comfortable. Okay. In this situation, it's going to be a slightly different problem because now the question mark is on the arithmetic side, the ordinary arithmetic side. Here we have 3 as being something that is in the character set, so we really don't have to worry about it. What we're going to have to ask ourselves in this case is, what makes 3 in ordinary arithmetic? So in other words, zero in on this chunk here. What is it minus 4 that would produce ordinary 3? 3 ordinarily. All right. You probably know, all right, is that this would have to be a 7. However, if we were content with that, and we shouldn't be, we'd have to check that, see that this is a positive that is less than the modular number in this particular scenario, right? So is 7 less than the modular number in this problem? It isn't, because positive 7 is not less than 5. That Modulus system is 5. So we have to find an equivalent. I'm a little short on space again. So what I'm going to do is I'm going to erase what I have here because I already did that, and borrow this space here from myself. This is the situation that we would normally be content with. Right? But 7 is not going to work for us. So what we have to do is try to come up with an equivalent for 7. All right. Earlier, though I erased it, unfortunately, what did I do to get outside the realm of negative? I added 7 to go through a complete cycle because that was the case mod 7 in part A. In this case, the number that I'm going to add, potentially subtract, in this case is a 5 because we're dealing with mod 5. So if 7 is something that is too big, essentially in this case, for that reason, right, because it's exceeding the modular number, then let's find an equivalent that is one cycle lower. That means that essentially I'm going to do 7 minus 5. Right? The number that I'm going to produce is going to be equivalent, right? It's going to look weird, right? But it will be, just cyclically speaking, one cycle lower than something that is too big, right? So what is 7 minus 5, right? In ordinary arithmetic, right, that would be 2, right? There happens to be a 4 sitting here, and we don't have to worry about anything else, really, right? Right? If you were to start from scratch, right, and you saw this handed to you, if you saw 2 minus 4, which would be a negative 2 under ordinary circumstances, right, you might get a little annoyed, right? But we're starting in a different place here than we were before, all right? You would especially get annoyed if you saw something like this. Imagine you have some relative standing around watching this and they're going, is this what you went to college for, right? 2 minus 4 equals 3. That's baloney. Fire that guy. In the modular system, that is mod 5, that's the way it is, apparently. How come? Because if we're dealing with mod 5 and 7 is too big, we have to go one cycle lower, all right? So that means subtract 5 rather than add 5 in this case to figure out what the equivalent would be. Right? So is this number 2 less than the modular number of 5? It is. Positive 2 is sitting here, is indeed less than 5. That's the question mark for this particular problem. Right? It's a little goofy, all right? But if you do enough of these, it starts to make sense, right? If your mind is corrupted, right? And then you go, all right, put me in a straitjacket. All right, one more of these and then we'll shift gears, right? We're still on the arithmetic side, all right? But we're looking for the figure that is to the right of the operation, all right? A modular 8 system to start with looks like this, okay? So, 7 is just a check, is indeed an element of a modular 8 system, so good. All right. We have to try to conceive of now a number subtracted from 5 that would produce 7, right? Well, there isn't one, right? If you had, the only number that, at least to match digits, that would come to mind is the number 12, right? But then you would get a negative 7, not what is actually there, right? So, all right. Let me just remind you of something, all right? If we're dealing with modular 8, in mod 8, all right, adding 8 results in numbers of the same modulo class, right? Which essentially means what? They're equivalent because they have the same remainder. They may look different, but they have the same remainder. So I'm going to need the space, so I'm going to erase this now. What we're going to zero in on is this number here. I'm going to have to basically enlarge this number, 5, because this number has to be a larger magnitude on the left side of the operation of subtraction in order to result in a positive here. So what I'm going to do is take this into consideration. I'm going to produce a number that is a cycle or two larger than 5, right? When you're trying to go larger, right, add 8 in this case. So if I have essentially 5 plus 8, and there's still this gobbledygook here, minus question mark equals 7. We'll see what we can get that works. All right. What would actually be 5 plus 8? All right. 5 plus 8 itself would be 13. All right. What is a number now under ordinary circumstances that would produce a 7? What would this question mark have to be in order to result in a 7? Right. Well, it would have to be 6, right? 6. All right. All right. That means that, although again it's going to look very strange, right? This problem of 5 minus something being congruent to 7 in mod 8, this would have to be a 6. Right? Again, any bystander would look at this and go, my God, how is this man so stupid? All right, that he thinks that 5 minus 6 is positive 7. But that's why it is imperative that you include this little addendum here, all right, that it is in mod 8 arithmetic, all right, not in ordinary arithmetic, otherwise you look like a cuckoo bird, okay? So, that's, in this case, we needed a number that would be larger than 5. So the best thing that you could do is go a cycle up or a cycle down. In this case, you're going to go a cycle up to go larger, add 8 in this case. In the last case, it was to subtract 5, and in the case before that, it was to add 7. Okay, so this is your figure. Let's just check to see that we're meeting the, conforming to the question here. All right, is this question mark of 6 a number that is less than the modular number in this case? The modular number in this case is 8, right? The question mark in this case is a positive 6, right? So yes, I know that there's a minus here, but that is the operation. That's not the sign of the number. All right, so good. All right, we found something that works. Right, there's a lot of mental flexibility is the bottom line when you're dealing with something like this. Don't be upset if you go, that makes nonsense. Remember, what is happening essentially is that you're shifting between doing ordinary arithmetic and doing this sort of alternative arithmetic here. All right, modular arithmetic, cyclical rather than linear. Okay. All right, I'm gonna make a little note for myself. Okay. All right. Now that's doing addition and subtraction. If you look at example 4, this is where you have multiplication. Again, I will rephrase this as best I can. Continue. At least to start out with, I'm going to divvy up the board here like so. I'm not dropping my t-square, hopefully. Not too far, anyhow. And we'll continue. I'm late today. This will be our part A here, hopefully, B, and C, respectively. All right. A similar situation, except that we're dealing with products in this case. Determine all positive numbers to replacements that are less than the modulus. So we need a number that is in the position of the question marks here, that is positive and smaller than the modulus in question. So maybe always start out with is easiest, right? The modular system, the way it would look here for mod 5, right? We want a certain level of familiarity here. So mod 5 means 0, 1, 2, 3, 4. Mod 6 is one number higher. 0, 1, 2, 3, 4, 5. And mod 6 again is the same thing. 0, 1, 2, 3, 4, 5. And Modulus systems begin with 0. That's why they don't have the actual digit. That is the modular number. Okay. If we had this situation to zero in on here, 2 times what equals 3? Under ordinary circumstances. There isn't a number that normally makes that, right? Unless it was 1.5, which we're not dealing with decimals. So what we have to do is check for things that have the same remainder, i.e. that they're equivalent. I need to highlight that. Right. equivalent to essentially remainder 3. All right, let's test what we have. Again, a little short on space here, but I'll try to squeak it in here first. All right. If it was 2 times, I'll put in a box here. Question mark. Two times 0 under ordinary circumstances produces a 0. Right? That's a character in the set here. Right? So that would not be equivalent to 3 per se. Right? 2 times 1 would be 2 itself, also a character in the set here, right? Which is not equivalent to 3, it's its own thing. Right? 2 times 2 would be 4, right? And that's the maximum. Right? That means that it's its own thing, right? It's one of the characters in the set here. Right? 4 is allowed to be written, but that's the absolute maximum. Right? If we went one number higher, we would have the number 3, right, under ordinary circumstances. What is 2 times 3? That would be 6. Now, what we're going to do is that since this exceeds the maximum, we're going to check what it's equivalent to. All right, and again, I need a little bit of space, so I'm going to write up here. All right. If I were to divide the number 6 by the modular system of 5, it would be 6 divided by 5, right? How many 5s can you squeeze into 6? 1. And 5 times 1 would be 5, so you'd subtract that, and then you'd have a remainder of 1. That essentially means that 6 is equivalent to 1, right? That's not 3 though, right? So we're going to continue, right? Just because I'm short on space, I'll put a little bit extra here. All right. What would be the next number? Would be 2 times 4 under ordinary circumstances, which would be equal to 8, right? Which also exceeds, so we're going to check the equivalent. Right? If I took 8 and I divided 8 by 5, let's see what we get. How many 5s can you squeeze into 8? 1. 5 times 1 is 5. Subtract these, you get 3. And lo and behold, we finally have a number that is the actual number here, 3. Right. That means that 8 is congruent to 3. 6 is congruent to 1, right? And 8 would be congruent to 3. Alright, now the one thing that you have to bear in mind here is that we're looking for something, a positive number that is sitting in this position on this side here, that happens to be less than the modular number, right? Right. So far, we have only one example here that is congruent to make a 3. Right. The number that we had is the number 4. Right. So, is positive 4 less than 5? It is. So that's a legitimate answer in response to this question. Right. If you did another one, look what would happen. the next number after 4 would technically be what? It would be 5. And in that instance, you would get 10, which again exceeds, so we would have to, exceeds the limit of 4 here. So we would have to check that as well. So if you did that, what would happen? Well, 5 divided by 10 would give you a 2. And then you would have 5 into 10 is 2. And then if you subtract them, you'd get a remainder of 0. Right? You'd get a remainder of 0, which isn't equivalent to 3, right? You would say that, yeah, 10 is congruent to 0, apparently. Right? Anyhow, that number 5 is not less than the modular number. So it would be pointless to continue with this, right? You could get other things that would end up being congruent to 3 potentially, right? But they're not going to satiate the requirement that the number that you've chosen that I have in the boxes here as being smaller than the modular number, right? So the only viable solution to these requirements is this. Essentially, the number sitting in this position that works, the number here that is also less than the modular number of 5 is 4, positive 4. 2 times 4 would produce 8, and 8 divided by 5 produces a remainder of 3. That's the only viable solution given these conditions. Let's do another again, because these are weird, right? So we'll do this one here. We're looking for something in the same position again here, but it's going to be in mod 6, and it has to be equivalent, have the same remainder as 0. So let's go through that, run the gamut of possibilities here. All right, if it was 3 times 0, all right, that would produce 0. All right, so that's legit. All right, save that one. 3 times 1 would be 3, which we're not going to use. Right? That's its own thing. It doesn't exceed 5 in the character set in the elements, so we don't want that one. And it's its own thing. What if we did 3 times 2? That would be 6. 6 is outside. This is exceeding. Right, so we check. Right, and since I'm short on space, I'll do this over here. We'll check to see 6. Um, 6 divided by itself would go into itself one time, and that would produce a remainder of 0. Okay, very good. That means that 6 is congruent to 0. So that this one is good. Let me put this in a different color just to make it more obvious. All right. 0 is doable, right? And apparently 2 is also good because is even though it exceeds the character set by 1, it just cycles back to apparently what represents 0. Right? So that's good. Right? We're still within the confines of the conditions of this problem. If you did 3 times 3, what would you get? You'd get 9, which again exceeds. So we're going to have to check that. 9 divided by 6. And what does that translate to? 6 goes into this one time, which is 6, and the difference is 3. This is a remainder of 3. Right? So that would mean that 9 is congruent to 3, which is not one of the requirements here. Meanwhile, we have to keep in mind that we only want those numbers sitting in this position of question mark, right, that are less than the modular number, which happens to be 6 in this case. So 0 is less than 6, that's fine to keep. 2 is less than 6, so that's fine to keep. All right, what's another one? 3 times 4, which would be equal to 12, and we'd have to check that again. So we have 12 divided by 6, which goes into this exactly twice, which is 12, and that's a good one. 12 is congruent to 0. Right? It's in the same modulo class, modular, or whatever you prefer. All right, so 4, also good to check. All right, 4 would be less than 6. We could keep it. All right. I think that's going to be the maximum, but here, let's check another one. We'll see if we've gone too far here. All right. Remember, the next one would be 3 times 5, and that would be 15. All right, certainly exceeding. All right, but 5 is the limit, right? So if I check that one, $15 divided by 6, it goes into that twice, which is 12. The difference is 3. That would be a remainder of 3, which means that 15 is congruent to 3. They're in the same modular class. Right? 5 is the limit because that would be the thing that is less than the modulus. If I did 6 itself, 6 might work, right? But I can't use it because of the original condition, and I'm looking for things smaller than 6. Right? So, what are the question marks that are legit in this problem? Right? What would be sitting here that would produce 0 in a modulus 6 system? 0 itself, 2, and 4, and that's it. Okay. Now, last one of these, C here, is still a modulus 6 system, but we have a different product here. Right? So we had done some of these already, because I had that. I'm going to rewrite them. I probably shouldn't have erased them, but here, I'll put them here. 3 times 0 is 0. 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. 3 times 4 is 12. 3 times 5 is 15. That's pretty much where we left off. Now, what we're interested in these cases is not something that is congruent to 0. We're looking for things that are congruent to 2. Instead. All right. Now, what ended up happening when we checked congruence was what? Right? 3, pardon me. already, if we use the actual numbers that are allowed here, 0, 1, 2, 3, 4, 5, all right? They're from the character set, the elements, right? This produces something that it's its own thing, so that's not 2. That's not 2, so that's not a possibility. Using 1 produces 3, which again is its own thing. It's not 2, so we're eliminating that as a possibility. If we use 2, that is the thing that exceeds, right? So we start exceeding after this point. Right? And what happened before was what? When we tested this, 6 divided by 6 results in what? A remainder of 0. So that means that 6 is congruent to 0, which means that this is not a viable possibility either. Right? If you test this one, 6 into 9, then what do you get? You get 3, remainder 3, which means that 9 is congruent to 3. That's not 2 either, so you can't use that. And then if you do this one and this one, what you're going to notice is that there's something of a pattern going on here. So, sorry for that. 12 is 2, and that's a remainder of 0, which means that 12 is congruent to 0. That's all fine and dandy, right? But that's 0, not 2, right? All right, and I'll do this one and then I'll stop. If you checked 15, 15 divided by 6 is 2, which is 12, and the difference is 3, and you get a remainder of 3, which means 15 is congruent to 3, which again is 3, not 2, what it needs to be. So what's going to happen if you were to continue is that you're going to get things that are equivalent to 0 or 3. 0 or 3. Right? Which basically means what? Right? There's no solution. No solution because there's no congruence to 2. Right? Right? Using the numbers that were allowed. So that's that. Nothing actually produces 2. Enough of that. All right, let's do a word problem. And I'll try to speed it up a little bit. All right, these are the examples of the word problem. 5. Now, you know what I did? I made a sort of a worksheet. I didn't give much of an explanation beyond the title of the PDF. Like it says, modulate, for example, 5. Let me point to it in the packet. This is something that's available as a PDF, right? The problem here says Dusty is a security guard at a shopping mall. Right? His work schedule is to work for 6 days, and then he gets 2 days off. Right? So the week is not a regular 7-day week. Right? It's essentially sort of an 8-day block. All right, that will cycle in 8s rather than the amount of 8 rather than the amount of 7. All right? If today is the 3rd day that Dusty has been working, determine the following. Will he be working in 60 days? Will he be working in 82? Was he working 124 days ago? Right? To do a problem like this, you need to first identify that you're dealing with a Mod 8 system, which means that this is the set of elements that you would have listed in roster style. Okay? So that's really the whole point of that piece of paper. All right. Now, let's make it as straightforward as possible to answer these questions. All right. Now, let me get some markers here, and I'll get rolling. All right. To reiterate what is being stated here, again, as the teacher, you must develop a level of comfort where you don't just tolerate things as they're given to you. You have to realize that maybe they're written A badly, or they're meant to throw a student. Right? Don't just accept things as they are. Within the confines of logic, take what is written and try to elucidate. Right? So we're talking about a person who has a work schedule. Basically 8 days in a row. Mm-hmm. What that would translate to, 6 days on, quote unquote, and 2 days off, is that you have a Mod 8 system. Right. How would that look? A Mod 8 system would look essentially like this, right, without pulling up the other slide. 0, 1, 2, 3, 4, 5, 6, 7. It's a little misleading, right? As we go, yeah, a week is 7 days. But remember, the way that it's discussed in this example is that you're talking about blocks of 8 rather than blocks of 7. Right? Now, what I would do to make this a little bit easier is put little labels maybe above here and below here, right, that are conforming to the other specifics of this problem, right? I'll look for abbreviations. The word on and the word off, unfortunately, start with the letter O, so I can't use that as an abbreviation, aside from the fact it kind of looks like 0. What I'm going to do is I'm going to say on means working. So we'll use the letter W there, all right? And off means not working. So I'll maybe use the letter N there, right? So we're gonna use maybe W's and N. If you started from scratch, right, day 0, right, then what you would have here is this, all right? On 0, the first day, it would be a W, you would be working, right? On the second day, you would be working. Third day, working. Fourth day, working. Notice that the fourth day, maybe I'll put in a different color here. First, second, third, fourth, fifth, sixth, seventh, eighth. According to their description, he would be, for the first 6 days in a row, we would be working in the coal mine, right? And then 2 days off, right? So N for not working, N for not working. Okay. Now, you could, if you wanted to, do what we had done when I was talking about the clock, all right? You could adapt it to, instead of it being like so, make a clock that is maybe W's and N's, right? But there would be 8 increments here rather than 7. All right. Nonetheless, that would be kind of tedious to have to do that to make from scratch. And when you're dealing with numbers like 60 and 82, a real pain in the neck, all right, to have to count forward or backwards. So what we're going to do is we're going to sort of modify this. All right. Problem A, part B rather, and part C. Okay. Determine the following. Will he be working 60 days from today? Right. If today is the 3rd day, right, what is the 3rd day represented in the modular system? If today is the 3rd day, then that means that is represented by the number of 2, right? Will he be working 60 days from today? Right? All right. Well, what we need to find is congruence in probably each of these cases. So I'm just using red because it stands out a little bit more clearly. All right, using this number, 60, to start with. All right, find the equivalence to 60. How do you do that? Well, you divide by the modular system. So, what is 60 divided by 8? All right, rather than count 60, because that would be a real pain in the neck, what we're going to do is get something that represents 60, which is going to be a smaller number, limited to just these digits. All right, how many 8s can you squeeze into 60 roughly? 7, right? So that's 56, and the difference of 60 and 56 is 4, so that is remainder 4. That means that 60 is congruent to 4 steps or jumps. We might say jumps, all right, forward. All right, so if today is the 3rd day in the schedule, counting from here, we're going to go 4 jumps forward, all right, because there's 60 days in the future. So where does that land you? 1, 2, 3, 4, all right? He would therefore be on the 7th day in the schedule, which is represented by 6, and therefore not working. So, A, not working. Good for Dusty. Okay. He's off. All right. More or less the same thing. Determine the following: will he be working 82 days from today? The condition of the day that you're starting with, being the 3rd day, hasn't changed. So, this is still the start, right, rather than 0, right? And what we're going to do is try to find equivalence between 82 and the numbers that we're allowed to use, 0 through 7. So, what is 82 divided by 8? All right. 8 goes in 82 roughly, well, in itself once, which is 8, and the difference is 0, bring down 2. 8 will not fit in 2, so we would put a 0 here. 0 times 8 is 0, and therefore the remainder would be 2. All right. Which means that 82 is equivalent to 2. Congruent, right? 2 jumps, again, forward. In the context of this problem, forward, I mean to the right. Right? So from here, starting still on the same 3rd day, 1, 2 would be day 4, the 5th day rather, but signified by the number 4, and the person would be working. So on B here, he would be, yes, working. Okay. All right. Day 5 is 2 steps from day 3. All right. That's the number 4, he's working. All right. Then this question, they toss it up, right? They say, well, what day was it on or off 124 days ago? All right, so that is implying the past rather than the future. So rather than going forward, we're going to go backwards. But we don't want to count 124 steps. So what we're going to do is find an equivalent to 124. And then just go the other direction rather than right, go left. So if you have 124 and divide by 8, 8 goes into 12 one time, which is 8, and the difference is 4. Drag down a 4. 8 goes into 44 5 times, which is 40, and the difference is 4. And this is a remainder of 4, so what that means is 124 is apparently congruent to 4 days backward. So, still starting on the same day, which is the 3rd day, just go backward. Now, it's a little bit of gobbledygook here, so let me erase a little bit of the mess that is present. All right, and just remind you of something. All right, here's where we're starting on the 3rd day, number 2, working. We're going to go towards the left, but because it is cyclical, I'm going to have to wrap around a couple of extra days here. So I'm going to go 4 days backwards. So starting here, 1, 2, 3, 4. It would end on what would technically be the 7th day in the block, represented by number 6, and in this instance it's a non-working day. So not working in this last instance. Okay. 124 days ago, Dusty had off. Good for him. Okay. Last problem, I swear. And this is filling in a table. So let me flash the question here. And then I'll walk you through the process. Okay. The exercise here is to construct a mod 5 table. Why? Because if you do that, it would make answering mod 5 questions theoretically easier. It'll be a little tedious at first, but it's certainly something that's feasible. Let me get a sip of water here. Without filling it. Construct a 5 mod addition table and show that the mathematical system is in fact commutative. So eventually what we're going to have to check is a couple of things. Remember, for something to be commutative, there are criteria. It has to be closed. Number 2, there has to be an identity element. All right, number 3, there has to be inverses for each. It has to be completely associative, and it has to be commutative. All right, those are the 5 criteria to pass for the qualification of commutative group. All right, it's a system, so it has an operation of addition, and it's mod 5. Right. First of all, what does that look like if we're talking about mod 5? Right. The set is going to look like this. 0, 1, 2, 3, 4. Right? In a mod 5 system, because remember, modular systems, you start with 0, and there are 5 total, so 1, 2, 3, 4, 5. The operation is going to be addition. So tucked up in the corner, there should be, in the table, there should be a plus. Assume that the associative property holds for the given operation. So therefore, we don't really have to check associative because it's a lot of different combinations. So already, this requirement is satiated. That means that we're just going to have to check these other things. All right. Now, how do you make a table? All right. Again, I did, in fact, give you a handout for this. Let me just obscure this. Quit. And draw up the blank here to walk you through it. Here's the blank. All right, the question, we already are aware of it. All right, we're trying to prove that if the mod 5 table is in fact commutative, right, the system, we need to construct the table, all right, and then check the criteria. All right, is it closed, meaning that adding, in this case, only produces 0, 1, 2, 3, 4. All right? If there is a proper identity element and if there are inverses present for each. Then we can check symmetry, because we're using table shortcuts in this case, all right, to do this. Now, if you're constructing a table from scratch, all right, here's a blank or mostly blank. The operation goes up in the corner here, because those are the things, that's the binary operator, all right. And the character elements, the set of elements 0, 1, 2, 3, 4, 5, should be the column headings in the consistent order, and also the row headings. So 0, 1, 2, 3, 4. I'll erase this because it's kind of obscuring. All right, but that's what I'm doing here. All right. When you construct a table, ask yourself, if it's mod 5 in this case, then what are the elements? These are the elements. They will therefore be the row headings and the column headings. And again, I like, not to pat myself too hard here, but I like my table better than the type you see in the textbook because I use colors. In theory, make these things distinct. All right? I don't know why they didn't do that in all cases, but hey, I'm not a publisher, so maybe I don't know. All right, now, we do have to do the arithmetic, all right, to verify what goes in these boxes, all right? At least a little bit of it until we perceive a pattern, you know, hopefully. So, this is going to be normal, all right, up until a certain maximum. Remember, the maximum is going to be 4. All right, so if we have anything beyond that, it cycles back. It cycles, all right? Okay, so what's 0 plus 0 under ordinary circumstances? Just to make this a little bit more distinct. I don't know if green is going to show up, but I'll try. All right. 0. All right, so you put a 0. That looks pretty good. All right. What's 0 plus 1 under ordinary circumstances? All right. 1. That's a number that's in the element set, so it's okay. All right. 0 plus 2 is 2. 0 plus 3 is 3. 0 plus 4 is 4. All right. So far, so good. All right. 1 plus 0. It's still going to be 1. All right. 1 plus 1 is 2. That's in the set. All right. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. Now here's the problem. All right. I'm going to put this in red and then I'm going to change it. That exceeds the maximum. All right. So, even though in ordinary circumstances 1 plus 4 is indeed 5, I can't write the number 5 here. I have to have an equivalent. Now, you probably know what it is anyway, but what would be the equivalent of 5? 5 would be equivalent to what? You test it in the modular system. You take the number 5, and then you divide by the modular number, which is 5. So, what is 5? All right. 5 goes into 5 one time, the difference is 0. The remainder is 0, therefore 5 is congruent to 0. That means that what has to go here is 0 instead. All right, let's go back to the beginning here. 2 plus 0, that's perfectly fine, that's 2. 2 plus 1 is 3. 2 plus 3 is, again, this would be 5 again. But we can't have that because it exceeds the maximum in the set, which is 4. So, we already did the work. What is 5 congruent to? It's congruent to 0. So what I would have to put here is 0 again. Now, you might be starting to go, there's a pattern here. oh, pardon me, I ding dong. 2 plus 2, 2 plus 3, I'm not reading the heading when it should be. 2 plus 2 is 4, that's perfectly legit. 2 plus 3 here would be 5, which we're going to replace with the legitimate symbol of 0. Okay. All right. Now, if we're now back at 0, you could probably guess what the number would be here, right? If you still feel a little nervous, right, go through the motions, right? 2 plus 4 would be what? 2 plus 4 under ordinary circumstances would be 6, but again, you have the same issue. It exceeds the maximum of 4. Right? So, to figure out what the equivalent is, you could probably figure it out, but what would be the equivalent of 6 in our modular 5 system? Right? Do the division, 6 divided by 5. Right? 5 goes into 6 one time, which is the difference of 1. That means that the remainder is 1. Therefore, 6 is equivalent to 1. Right? That means that instead of using the number 6, you're going to put the number 1 here. Okay? And now, again, you could do the arithmetic, or you could start to see that there's a pattern unfolding here. What will happen is this, right? 3 plus 0 is still legitimately 3. Look at this column here, all right? Because it's mostly filled in this direction. It's just 0, 1, 2, 3. Without even doing the arithmetic, you can bet that this is probably 4, all right? 4 plus 0 is 4, so, good, all right? Again, if you're a little nervous, check. 3 and 1 would be 4. That's a legitimate number to use. All right, and look at the pattern that's unfolding here. 1, 2, 3, 4. 4 is the maximum. What's probably going to go here is 0. Well, let's just check. 4 plus 1 would be 5 under ordinary circumstances. We've already concluded that 5 is equivalent to 0. So that would be there. 1, 2, 3, 4, back to 0. It cycles back. The maximum is 4. Beyond that, it cycles back, right? Because it's a finite system, right? Modular systems, all right? You could probably bet 2, 3, 4, 0, and then it would be 1 again. But if you're uncomfortable, check it. 3 and 2 would be 5, all right? 3 and 2, if that is 5, we already have decided is equivalent to, or determined is equivalent to 0, right? So, 0 again. 3 plus 3 would be 6 again, right? And 6 we already have determined is equivalent to 1. So that would be 1. All right? And just to make these distinct, 1. And then 3 plus 4 would be the one example first that we haven't done yet, which would be 7. All right? Again, if you wanted to check, here's 7. 7 divided by 5 goes into itself once here. Goes into 7 once with a difference of 2. This is a remainder of 2. Therefore, 7 is equivalent to 2. All right, that's intuitive. All right, 3 and 4 is 2. All right, and it would continue, right? Right. 4 plus 2 is 6 again. What is 6? We already know that it's 1. 4 plus 3 is 7. We already know that it's 2. All right, you can probably guess that that's going to be 3, and it is. Right, because 4 plus 4 is 8. 8 divided by 5 is a remainder of 3. So 8 is congruent to 3. Right? And that's the whole table. Right? Now, having gone through that trouble, I'm going to clean it up just a little bit. We can now check for these conditions, that it's closed, that there's an identity element, that there are inverses, and that it's commutative using table shortcuts. Remember, table shortcuts are something that was established last time. Let me just flash it really quick for reference. Here we go. when we did section 9.2, we established, we established shortcuts when you're given tables, right, to check if something is closed, identity elements, if there are inverses, and whether it's commutative. Right? That's often why they just simply, tell you something is associative, so you don't have to torture yourself too much. Right? Now, I'm gonna, since we took the time, all right, to construct the table, I'm going to now show you the copy that is the nicer one rather than the scribbled one here. Right? I want to make sure that everything is cool. All right, 0, 1, 2, 3, 4, 1, 2, 3, 4, 0, 2, 3, 4, 0, 1, 3, 4, 0, 1, 2, and 4, 0, 1, 2, 3. That looks like it's legit. Good. All right, so having gone through that, here's the nicer copy. All right. You can apply the shortcuts. We already know that it's associative, so we don't have to check that again. All right. I mean, the eraser works not as well as my finger. All right. Now, when you're checking to see whether the system is closed, right, under the operation of addition, what you have to see is check to see that there is nothing extra in the table, meaning no other characters other than 0, 1, 2, 3, 4. We already kind of took care of that anyway because we found the congruent of 5, the congruent of 6, and the congruent of 7, and ultimately 8. So is there anything in the white portion of this grid that is beyond the number 4? Not anymore. So, is the system closed? You could say for certain, yes, it's closed under the system. It doesn't produce anything but the same type of elements. Not adding, at least. Now, the identity element. The identity element, the trick here is that you want to basically look for the row and column heading in the table. So, if this is the row headings here, 0, 1, 2, 3, 4, where do they appear exactly as such in the actual white area? They show up here. All right. Now, I'm going to also look for the column heading, which has got to be the exact same thing in the same order, but I'm going to be looking for it in the table. All right. Where do you see in sequence, the correct sequence, not botchable, all right, 0, 1, 2, 3, 4, all right, right here, 0, 1, 2, 3, 4, all right, where they cross is the identity element. So, where do they cross? They cross at the point of 0. All right. So 0 is the identity element, and it is present and accounted for. So far so good. All right. Now as for inverses, remember this formula. All right. The identity element would be equal to each element combined with the operation. So something plus something has to equal 0. Right? Since the operation is 0, we're going to check to see what equals 0 here multiple times. Right? And that there is in fact an inverse for each element. So if the elements are 0, 1, 2, 3, and then I gotta do it again, sorry, 4, we need to verify, hopefully that's visible, and if it's not, let me see if I can help that. It might be a little bit better. green kind of stinks. I mean that not in the literal sense. I mean it's not easy to write with it. What added to 0 equals 0? Right. 0, the green are the elements. And this is the identity element. Let's check to see what the inverses are if they're present. Right? 0 plus 0 produces 0. Right? Look and circle, maybe here's a good point. Look for all the zeros now. And I'm going to circle them since those are the identity elements. What produces these? Right? 0 plus itself. Right? 0 is its own inverse, apparently. 1 with 4. 1 plus 4 is 0. Again, this is funny why it is nice to have a table, because remember that logic defies logic, right? Under ordinary circumstances, 1 plus 4 is 5, not 0, right? But we already took the time to make the table, so we know it's cyclical, all right? So having the table to go, those are the zeros, all right? We can connect them to identify what the inverses are. 1 is the inverse of 4, right? 2 is the inverse of 3, right? 3 is the inverse of 2, right? And 4 is the inverse of 1, right? These are the inverses. These are all the elements. Are there inverses for each element? There are indeed. So that qualification, that criterion is met, right? One more thing we could check is that it's commutative. If in fact it is commutative, right, then there should be symmetry about the main diagonal. The main diagonal is from the top left to the bottom right. So what we would do is draw a line connecting these two corners essentially, and then see if it's something like a mirror, you know, on opposite sides. It's a little bit messy, so try to do this neat. This is a little slippery, sorry. And I'm standing in the way of it, unfortunately. All right. Do you see the same figures on opposite sides of this diagonal line here? All right. 1, 1, 2, 2, 3, 3, 3, 3, 4, 4, 4, 4, 0, 0, 0, 0, 1, 1, 2, 2. It has symmetry, right? So, indeed. Right. This is commutative without having to check all of the possible combinations. We're just taking advantage of that table shortcut. Okay? And that is, I believe, that. Okay, so let me turn this off. We're at 2.5 hours there, and I gotta go upload this now. And just remind you of what your homework is. All right. This stuff is a bit alien, so again, I would not wait until the last second to start doing this, right? In my lab. Homework, please do section 9.3 in my lab, right? Don't wait. Right, not on this stuff. It's a little, as you could tell, it took me 2.5 hours to go through this thoroughly. All right, you don't want to wait until the end of the semester when you have your final, okay? So just do that and you're good to go. Okay? Thank you guys for sticking with me. I'll see you again on Thursday. Be careful out there.